In this video, we're going to learn about Laplace transforms. So to start with, I want to talk about understanding versus accepting. When you learn something new, it's good to develop a clear understanding as you go. However, this is not always possible. Sometimes you just need to accept what's been described and then hope that the understanding comes along later. Laplace transforms are like this for many people. When you first encounter Laplace transforms, they're strange and nonsensical, and they don't really make sense. So what we're going to do in this video is we're going to look at all the different little bits of pieces that need to be fitted together in order to try and understand the whole thing, and then hopefully it will make sense by the end. So to start with some historical context, the Laplace transform is named after Pierre-Simon Laplace, 1749 to 1827, who was a French scholar and polymath. And around this time there were lots of scholars who were working on mathematical problems just out of interest, just out of curiosity, and seeing what would happen with different equations. And Laplace was not the first person to think about these sorts of ideas, and he wasn't the last person. So there was a lot of groundwork already laid by other people that helped Laplace to devise these ideas, and then the Laplace transform has been further developed since Laplace. But Laplace was really pivotal in actually coming up with some crucial ideas, realizing the potential, the properties, and developing things further. Now, he was interested in Euler's work with integrals for solving differential equations. So Euler had published some work that used an integral of the form shown here, z equals integral of e to the ax, and then a function of x dx. And so this was one of the ideas that Laplace was exposed to. Laplace was also interested in and wrote extensively about generating functions. So he didn't use this exact notation, but it was the idea of having the sum of an infinite series, an infinite power series. And he sort of was influenced by these ideas and came up with his Laplace transform based on this. And as I say, he was pivotal in actually not just trying to use this integral to solve differential equations, but actually using it more as a transform. And we'll see what that means as we go through. So the Laplace transform of a variable that changes as a function of time, y of t, is defined as follows. So we have capital Y of s equals, and then we have this symbol here, which is the Laplace transform operator. So we're saying we're taking the Laplace transform of y of t, and to do that we take the integral from 0 to infinity of y of t, the function that we're interested in, multiplied by e to the minus st dt. So this is what he came up with. This is the Laplace transform, and we're saying that capital Y of s is the Laplace transform of y of t. Now, for the sake of consistency in this video, we're going to use a capital letter as the Laplace transform variable of s, and we'll use the same lowercase letter to denote the function of time as shown here. Now, this s variable is the Laplace transform variable. It can be a complex number and sometimes gets referred to as a complex frequency. And the units of this are inverse time. So now that we've got this definition, we can sort of try different things out with it. So if you think back to what I said earlier, you know, this was perhaps looked at as a bit of a curiosity, and we want to just sort of explore what it can do and think about what it can sort of give to us in terms of solutions to maybe ordinary differential equations and other things like that. So let's see what we can do with this. So first of all, let's look at what happens when we take the Laplace transform of a constant. So we have y of t equals a, where a is a constant. So if we were to look at a graph of y of t versus time, it's just a horizontal line. And so we have capital Y of s equals Laplace transform of a. We put that into the integral, and then we're going to have to evaluate that. So y of s, when t equals infinity, we can put that value of t in and we just get 0. When t equals 0, e to the minus st will go to 1 and we just get minus a over s. Tidying that up, we get a divided by s, and so that is the Laplace transform of a constant. Next, we'll have a look at the Laplace transform of a step. So this is where we have y of t is 0 for all values of time less than 0, and y of t equals 1 when time is equal to or greater than 0. So it's basically a step function, and you can see a graph of that there. So we're going to take the Laplace transform of y of t, put that into the integral, and you can see from the graph that where we're integrating from 0 to infinity, that y of t just equals 1. So we get minus 1 over s e to the minus st. And again, we have to evaluate that when t equals infinity, which will give us 0, and when t equals 0, which gives us minus 1 over s. Tidy that up, we get 1 over s. So again, we're just doing this to see what happens when we put different values in. Next, we can try an exponential. So we've got y of t equals e to the minus bt, where b is a constant. We take the Laplace transform by putting that function into the integral. We can tidy that up a bit by having the integral from 0 to infinity of e to the minus b plus s times t dt. So if we integrate that function and then evaluate at t equals infinity, we get 0. When t equals 0, we get minus 1 over b plus s. Tidying that up, we get 1 over b plus s. So we can keep doing this for different functions, and then we can tabulate the results. So rather than having to do this every time when we get a new function, or we want to go back to one of the functions that we've already integrated and done the Laplace transform for, we can just come to our table and take a look at what we get. So here's some examples. This also works if instead of just having like y of t equals 1 or the step equals 1, you have a constant. So if any of these functions are multiplied by a constant a, then the Laplace transform is just multiplied by that constant as well. Which brings us on to an interesting property of Laplace transforms. And this is the fact that Laplace transforms are linear, so they have linearity. So if we have a Laplace transform of a constant times y of t, it's the same as saying a times the Laplace transform of y of t. So overall we just get a times capital Y of s. Laplace transforms are also additive. So if we have y of t plus x of t, then that's the same as taking the individual Laplace transforms and summing them up. Okay, let's move on now to do the Laplace transform of a derivative. So remember, we're just trying out different things. We've got this new tool, this new integral, and we're just trying to see what it'll do for us, see what happens when we try and plug in different functions. So if we have the Laplace transform of dy by dt, we can plug that into the Laplace transform integral. So we integrate from 0 to infinity, dy by dt times by e to the minus st, and we're integrating with respect to t. So we have dt at the end. This can be solved using integration by parts. So here is the equation, the integral for solving by parts, and what we can see is that we need to change it from just a generic from limits from a to b from 0 to infinity. And then for our u of t, we're going to select e to the minus st. So our u of t equals e to the minus st. And then for our dv by dt, we'll plug in dy by dt. So we've also got that. Now we need to differentiate u of t. So we get du by dt equals minus s e to the power of minus st. We also need to integrate the dv by dt. So we just get the function v of t equals y of t. Okay, so now we can start to plug some of these things in. So first of all, let's look at u of t. Well, u of t equals minus st, so that will go into these square brackets. V of t equals y of t, so we'll plug that in. And then in the integral, du by dt is minus s e to the power of minus st, so we'll put that in. And finally, v of t gets substituted with y of t. So we've now got an equation that we can sort of work our way through and try and work out this Laplace transform of a derivative. So the first thing that I've done in terms of simplifying this is take the s outside of the integral. So previously that was minus s times e to the minus st, but I've taken the s outside because that's not affected by the integral, and because it was a minus minus, we can make it a plus. The next thing that we'll do is we'll evaluate the terms in the square brackets. So when t equals infinity, that will go to 0. E to the power of minus st when t equals infinity will go to 0, and so the whole thing is just 0. When t equals 0, we just have y of 0. So t equals 0, so we just get minus y of 0 there. Next thing that we'll look at is this integral here, and what's interesting about this is that this is just the definition of a Laplace transform. So we can just substitute in capital Y of s for that term. And of course, we also need to have the plus s. The s is multiplying that. So for completeness, we put that in. If we tidy up, we end up with Laplace transform of dy by dt equals s times capital Y of s minus lowercase y when time equals 0. And what's really interesting here is a bit of an aha moment, a bit of a eureka moment, because we've just changed a derivative into something that doesn't have a derivative. This is just an algebraic expression. And this is really the power of Laplace transforms, is that we can use them to take differential equations and turn them into algebraic equations that can be solved. So let's take all these different pieces that we've gone through and try and put them together to see how we can use Laplace transforms to solve ordinary differential equations. So we're going to look at an example. So the example is tau times by dy by dt plus y of t equals a, where tau and a are constants, and the initial condition y of 0 equals 0. So we've got the information, and we're going to try and use Laplace transforms to solve this. So the first thing that we're going to do is we're going to take Laplace transforms of both sides. So we've got this stylized L symbol, which is the Laplace operator, and as you do with algebra, rearranging equations, whatever you do to one side of an equation, you do it to the other side. So we're taking Laplace transforms of both sides. Now we're going to use the fact that Laplace transforms are linear, that they're additive, to just sort of break apart the left-hand side. So we've now got tau or tau times by the Laplace transform of the derivative plus the Laplace transform of y of t. So we're going to use this and actually think about the information we had in the tables and try and make progress. So the Laplace transform of a derivative is multiplied by tau, and so we need to bring that down. And from the earlier slides, remember we said that the Laplace transform of dy by dt is s times by capital Y of s minus lowercase y of 0. So we can substitute that in from what we saw earlier. Now Laplace transform of a lowercase y of t, we can just put in capital Y of s, and then for the constant we just get a divided by s. Now if you remember, when we set the problem up, we said that the initial condition y of 0 equals 0. So we can use that to tidy up the equation. And if we do that, we end up with tau s capital Y of s plus y of s equals a divided by s. Now, if we factor out the y of s, this is what we get. and then we can divide both sides by tau s plus 1, and that gives us y of s equals a divided by s brackets tau s plus 1, and we've now got a function in terms of y of s. So that's a really crucial part, really crucial step, is to rearrange and get y of s. The next part will then be to do the inverse Laplace transform. Now this is not something that we've talked about yet in this video, but let's sort of see what happens. So the symbol for this, so it is the Laplace operator to the -1. So this is to represent that we're doing the reverse now. So we're trying to go back from being in the Laplace transform variable and trying to get things back into a variable of t, of time. Okay, now the way that we tend to do this is by looking up in our table and seeing if we've got a function that's similar to the one that we've ended up with. So have we got something that looks like a divided by s times by brackets ts plus 1, close brackets. So let's go back to our table for a moment, and yes, there was an example there. So what we can do is the inverse Laplace transform is just saying we go back to the function that we had before. So we can use this information to get the inverse Laplace transform. So for our capital Y of s, that just goes back to y of t. And then for this function here, we write in a brackets 1 minus e to the power of minus t over tau. And just out of interest, if we were to plot this, this is the sort of graph that we'd get. So that is how we can solve ordinary differential equations with Laplace. And that is one particular useful example that we actually need when we apply this particularly to process control. Now, Laplace transforms are very useful for analysing process dynamics and designing automatic control systems. So Laplace transforms, as we've seen, can be used to convert differential equations into algebraic equations. And those algebraic equations are easier to solve than the original differential equations. The generalized process that we've used then is summarized in this diagram. So we're starting off in the time domain. So we have differential equations and initial conditions. We then use that information to take the Laplace transform. So that's step 1. Step 2 is then to solve for y of s. And then step 3 is to take the inverse Laplace transform. So we get a solution in terms of y of t. So I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.